Mm-hmm.
Do you guys see that?
I got a message that it is being that I did. Okay. Hello, everyone. So welcome to my talk. The talk is about a slice of the work I did during my PhD and where I worked towards explainable artificial intelligence and especially about my work with probabilistic prime implicants to interpret neural networks. So why have I called you here today? So since around 2012, neural networks have become the de facto standard in AI. That was the time when basically the ImageNet challenge was crushed by the net entry, and first time where these very deep models with convolutional layers, ReLU activations, and GPU training made their entrance to the stage, and they dominated the vision field ever since. And they have then advanced to other areas. They have phenomenal success in medical applications, protein folding, even abstract games for the first time, making it possible to beat human players. Here you can see the defeat of the Go champion against the AlphaGo model. And increasingly, these intelligent systems are also applied in really crucial applications. So what I mean is they make criminal justice decisions, like should people go on probation or do they get bail? They drive our cars, at least in prototypes, and it may well be that they do that in the near future. And they also make hiring decisions for bigger companies. So they impact an ever more increasingly important part of our lives. And the question is, how can we understand their decisions? The problem is the most accurate model, these are these very deep neural networks, operate basically as black boxes. And the stronger they become, the less we are able to understand them. This has then birthed the field of XAI, which is explainable artificial intelligence, that also a lot of the people here today are a part of. And let's take a look at how neural networks think. So here you can see a schematic of a neural network. So you have some layers alternating during a linear transformation and some component-wise nonlinearity. So let's do a very quick definition. So we have like some depth L, and we define the neural network as going from the input dimension, the output dimension, alternating linear or fine linear transformation, and some component-wise nonlinearity rho. And for the purpose of this talk, we're just gonna assume that rho is the ReLU activation, which has become the de facto standard. And so this network has potentially a lot of parameters, and tracking the reasoning process of this network is very difficult. For example, GPT-3, people who work in natural language processing probably know this model. It's one of the deepest and parameter rich that exists. Has a lot of layers and parameters. So any method of interpretation that doesn't scale well with the parameters will ultimately fail because they are just too deep. Some first step that has come to the forefront of explainable AI are these so-called saliency maps. And they basically ask the question, which part of the input was relevant for a specific decision? So here's a little illustration of this. Here we have a classifier that classifies digits trained on the MNIST data set. And on the left side, I've drawn some, you can draw some digits yourself online in the link that you see at the bottom and let them be classified. And they also give you a heat map of what they think the network looked at. So I made this crude of a digit that's right at the border of 3 and 8. And on the left, you see the output of the network for 3. So it likes the dent at the right, and it likes the openings on the left, but it doesn't like that the middle part is a bit elongated. So there it gives like negative values. And for the output of the 8, it also likes the dent on the right because both 3 and 8 have this dent. It doesn't like these openings, and it does like these elongated parts. So you kind of see what favors the decision for 3 and for 8 respectively, and what speaks against these decisions. And you might well say, okay, this is nice, but it's not really an explanation of what the network does. It's more like, okay, where it looks. And that is true, but already these simple methods can be used to investigate how some of these networks or classifiers in general work. So for example, we used them here on some data sets that classified, for example, boats. And we saw that some classifiers here, the Fisher vector classifiers, only looks at the water, whereas the steep neural network actually looks at the boat. So we see that probably the Fisher vector classifier will not generate well, and it's rather an artifact of the data set that has boats always on water. Or even more interesting, here we had some pictures of horses, and the Fisher vector actually learned to recognize a source tag that was on the lower left of the images. Of course, we expected also not to generalize well. So already these heat maps give us some idea about what the network does. We used this in a bigger project where we basically trained small networks to play Atari games. So here you see the game Breakout, where you have like a pedal and a ball that you reflect, and where you want to hit away at some colorful wall that gives you points. And we can track over time what the network focuses on. So in the beginning, the pedal and the ball, they don't have a lot of weight. And then during the training, they gain more and more weight. And at some point, you can even see that the network focuses on more advanced strategies, such as the tunnel. That's the region on the left and the right edge of this rainbow wall, where it tries to build a tunnel and then kick the ball through such that the ball always bounces on the top of the rainbow and the top of the game, so that it gets a lot of points without having to basically interact with the ball. And you can track these behaviors even before they appear as played, because the network first learns to recognize the objects and then learns to interact with the objects. So you can kind of track already if it recognizes certain things before it's able to interact with these things. All right, so I think we have seen that these maps are indeed useful. So what do we want to do now? So what are we aiming for? So what we aim for is we want to have a really precise definition of these saliency maps, and want to say what properties do these maps have? Because what you've seen so far, these maps, they only exist heuristically in the sense that they're defined by the algorithm that produces them. So it just says that here's an algorithm, do this and this, and then you get this map. But it doesn't really tell you what that map is and what properties that map should have. Then after we have the definition, we want some practical algorithms that do produce these maps. So what you've seen so far was a practical algorithm, but not according to any definition. And then we want also ideally to have some guarantees for these algorithms, so that we can be sure if we do these and these steps, we will get the properties that we defined before. All right, that's basically what I'm going to talk about in this talk. So part one is about probabilistic prime implicants. First, let me say a bit about prime implicants. They are a concept from logical abduction. I'm not going to go into the definition of prime implicants because it's a bit abstract. Let's rather use prime implicant explanations that have been introduced by Shi and Choi, Shi and Darvish. Let's assume, for example, that you have a function that tells you whether in a binary string there is a contingent string of 3 zeros. So on the right, you see, okay, there is a contingent string of 3 zeros. So the function says 1, it has found something. And then for a prime implicant, for the in part of the input to be a prime implicant, that means if we hold this constant and no matter what the rest is, the function will always give you the same output. So of course, these 3 zeros that you see there, they are a prime implicant explanation for this function output, because no matter what we put on the left and the right to it, it will always give you an output of 1. Of course, something like these 4 zeros would also have been an implicant, because it also implies that the function would be, output would be 1, but it would not be a prime implicant, because I could kick out the zeros to either the left or the right side and still have an implicant. So for a formal definition, say we are giving a binary function and some input assignment x, and then we call basically as a part of the input xs an implicant, if basically for every y that we could choose, it follows that if y is equal to x on S, then the function output will always be the same as before. And a prime implicant, additionally, if no subset of S is also an implicant. So if it's kind of subset minimal, you cannot kick out any more indices out of the set S. So the thing, what we did, because this is a nice definition, but it's not exactly 100% useful for something like very high dimensional nonlinear functions like neural networks, because these systems are very fragile. So there will always be some assignments to the rest of the variables, even if you have a good implicant that will basically change the classifier output. How can you see this? So there are actually these a bit on the fun side are these stickers that are kind of super stimulus for certain classes. So if you have a network, you can optimize these stickers to basically always change the network output to a different class. So the sticker there is like it's an image of a toaster, and it's designed in such a way that the network, whenever it sees the sticker, will say toaster, no matter what else is in the image. So basically, if we kept with this definition of prime implicants, we would always have to use almost all of the picture to have this property, because every small part could be manipulated to change the network output. That's why we said, okay, let's do this more probabilistically. Now we say, okay, it is like, we call this a delta relevant set. If conditioned on y agreeing with x on the set S, it has a very high probability of still giving the same function output. So for almost all possible assignments to the rest of the pixels, we still want the function output to stay the same. And then only a very small amount of these would be these, of course, adversarial patches, but they would not count very strongly in the overall distribution.
Stefan, sorry, Stefan, do you want people to ask questions as you go along, or would you rather that the questions come at the end?
I think I would love it if there are questions along the way, because normally in the end, everyone has forgotten their questions or doesn't care.
Okay. All right, so let me ask the first one then about this. I mean, if I take your example here, for me, this shows just to me that the classifier isn't very good. I mean, we have a good prime implicant. It's this damn sticker here that is basculing, is moving the classifier to predict toaster, right?
Yeah.
And so I don't think it's a problem with the prime implicant. It's rather a problem with the classifier. It's just attuned to the wrong kind of thing, kind of like your Fisher vector that you had before.
So that is a good point, in the sense that, yes, we don't have these classifiers that really work reliably well as humans would. So there will always be these adversarial attacks that can change either small parts of the image or the overall image by a very small amount, and that give you completely different classes.
Right.
And the problem is, the definition would make then more sense if we had access to classifiers that are really as well trained as what you want. The problem is, the thing is that we already want to explain the classifiers that we have. And at the moment, there is no way to basically build the classifiers in such a way that they are robust. Right. So that they don't have this property. At the moment, it's not possible.
Okay.
So, and that's why we said, okay, let's change the definition to something that is useful for the classifiers that we have at the moment. And in a bit of a different sense, even if they would be, even if they would operate perfectly, like recognize the images always perfectly, and you would have a network that differentiate between maybe a cat and a dog, and there's a dog on the image. If there would be a cat and a dog on the image, if I just add a cat, then the network would, of course, be confused. So if you have it, maybe I want to say something more at the end of this. What might be some ways around this? Maybe remind me to go.
Okay, that's very interesting. Yeah,
because I want to get too much into it at the moment.
Okay, great. Thanks a lot.
All right. So, and what we also want is we want to use continuous functions for this. So, like complete equality is then unrealistic because we are given a probability value between 0 and 1. So, what we replace this with is rather an expectation value over quadratic distortion, which, if this probability distribution big V is the same as binary, and phi are also binary functions, then this reduces to the property that we see here in the definition of the delta relevant sets. A bit of a different way to look at this is this rate distortion viewpoint, where you can see this task as finding these small probabilistic delta relevant sets as a communication task between two parties, Alice and Bob. So Alice and Bob share a classifier phi, and Alice wants to convince Bob that the image that she has is the class that she classifies. So the image is an ape, and she has only a limited rate of pixels to send to Bob. Then she wants to select some pixels that, for a probabilistic completion that Bob does, will still with high probability convince him that this is indeed, for example, here a monkey. And we can simulate this, we can describe it a bit as this. So we have some noise vector, we have some distribution V of S, meaning that Y is the same as X on S, and is the same as the noise on the complement set. And then we can define the distortion that Bob gets as just the expectation of the quadratic difference between those classifiers of the original phi of X that Alice has and his phi of Y that Bob gets. And then we can define this rate distortion function. Basically says for varying rates of distortion that we allow, what is the smallest amount of pixels that we have to send over that achieves this rate. And this idea basically is just the prime implicance over varying, like the probabilistic prime implicance over varying rates. Since we have this delta that tells us how strong our requirement is, there will be a corresponding set size that fulfills it. And so we get this rate distortion trade-off between the rate R and the distortion D of S. And there's a certain region where this is feasible to achieve. And now we can give an interpretation to these relevance maps that we've seen before, because these relevance maps don't really only do a binary decision between relevant and irrelevant, but rather they kind of rank all the pixels by their relevance. And we can interpret them as a greedy approximation of the rate distortion function, named in the sense of, okay, you want to get below some distortion of epsilon, just take the k, just take the highest ranked pixels until you are below epsilon, and then you can see at how close does this come to the optimal rate. So, for example, here I've painted this picture of a cat. For varying rates of epsilon, you could imagine that the set S becomes larger and larger as epsilon becomes smaller, and then you get a kind of a ranking of the pixels in their relevance. And then you can compare this rate distortion function of the greedy approximation according to the map with the optimal one. Of course, it will not reach the optimal one, but the type of guarantees that we would like to have would be that it isn't too far away from this optimal one. That there's, in some sense, it still selects reasonable pixels for this task. So that is basically the definition that we have. What properties do we want? We want these maps to well approximate these optimal rate distortion functions. Now let me go to 2 and 3. We want practical algorithms that produce these maps, and we want also guarantees for these algorithms. Sadly, as we will see now, it is the case that we cannot have both because there are some complexity results that I want to talk about now that basically say practical algorithms will not give you reasonable guarantees. So that's part 2, computational complexity of the task. So for these data relevant sets, we can define the following task called data relevant input. If we are given a Boolean circuit phi and an input x and a k, can we decide there exists such a set that's smaller than k and that is also data relevant? And what we found out is that this problem is actually NP to the PP complete. So that means like an NP Turing machine, non-deterministic Turing machine with a PP oracle. And this is actually a complexity class that is common for AI tasks because it describes situations where you have an agent with a plan. This is the NP part, interacting with some random behavior of some environment. This is the PP part, and you want to kind of bound the success probability whether the agent can find a plan that achieves this goal. And yes, just probably a lot of people know the definition of NP. So it's just that every language is an NP if there's a non-deterministic Turing machine M, such that for every word in L, at least one of the paths of M accepts this word. So X is the word in L. And PP is the same, basically, just that instead of at least one path of M, the majority of the computational paths of M have to accept X. And that's an even stronger class than NP. So, but we can make the problem maybe a bit simpler. I mean, first of all, we realize that calculating expectation values is hard in principle, but it's something that we do basically every day, and it shouldn't be like what's keeping us from by introducing some computational hardness. So what we do is we say we introduce the promise of a relevance gap. So for this decision, you don't have to decide whether it's really higher or equal to delta or lower or equal to delta, but instead we introduce a little bit of a gap here and say, okay, you only have to make the decision if it's higher than delta or lower than some delta minus gamma. So there's a gamma gap between these decisions. And then you can easily do it with sampling. Even if the sampling values accumulate around delta, you can still make the decision that it's not smaller than delta minus gamma. Increasingly with more samples, you will get surer of this. And this puts the problem in NP to the BPP. So something that you only need a sampling oracle. Then we say, okay, we don't need the exact set size to be right. We say, okay, we just want an approximation of the optimal set. So for example, if this is an image and S star is the optimal set, we say, okay, something like this S1 would be fine as well, where we just, S is inside and it's not too much, not much larger. But something like this S2 would be not good because it covered almost the whole image. So that would not be of use. Then we are not smarter than before. And so the end decision becomes only between basically, yes, there are small sets that are very relevant. So this is the yes gradient, or no, all large sets, all sets up until some polynomial in K are not even delta minus gamma relevant. So this is the only that you have to make. But we have shown that even in this scenario, this problem is still NP hard. So that led us to this inapproximability result that we won't find we won't approximate the optimal set even to a factor of delta of d to the 1 minus alpha for any alpha between 0 and 1. Of course, if alpha was exactly 0, then we would have an approximation factor of d, which is the input dimension, and that it's trivial. Just say the whole input and then you're done. But any non-trivial factor is basically NP hard. And that also carries over to continuous distributions and to continuous functions in our rate distortion framework. So also there, for this rate distortion function, we will not get a non-trivial approximation factor. And that means this guarantee that we would like to have will probably not come about, at least not for efficient methods, and at least not if we don't restrict the function class anymore. But this proof can already be achieved with weights of between -1 and 1 and of 2 layers. So there's not much that you can restrict further. Question, can we just do it anyway? Let's see. So we've seen, okay, practical algorithms and guarantees for these algorithms will not work together. Let's change the task a bit to practical algorithms. Well, they are still useful. And then instead of a priori knowing that they produce good results, we just have to test them afterwards through numerical evaluation. And now I want to talk about the second part. How can we design these practical algorithms? All right, heuristic solution strategies. Let's recall the rate distortion viewpoint that we had here between Alice and Bob, where Alice searches for some set of pixels. Now we want to do a convex relaxation for this set membership. So in the discrete problem, we say, okay, we want a relevant set, a subset of the set of all pixels. Now we say, okay, let's just optimize over a continuous relevant score, that is a score between 0 and 1. And instead of like having this binary decision between you're in or you get replaced with noise, we say, okay, we have a convex combination of the actual input and the noise. The distortion now doesn't depend on the set S, but rather on this vector small s. And the rate we give a convex relaxation of set size. In this sense, this is just the one norm, it's the complex hull. So now we get this new optimization. So we just use the Lagrangian formulation for some parameter lambda, minimize both the distortion and the set size subset subject to the S should still be in the binary cube. And basically, then we interpret these S as the relevance values, because this goes back to the interpretation that we can kind of threshold them and then always select a different part of the image or a set for this for the distortion that we're aiming for. And we have called this method that comes out of here rate distortion explanation. So this is kind of like the method we have put forth to interpret these new networks. One problem though remains a bit, how can we even calculate the expectation when we input the noise? Because calculating expectation values is hard. One possibility would be just a generic approach of sampling. But for something high dimensional and nonlinear, this would need a lot of samples and will become computationally quite expensive. That's why we have used, since we're in the vein of heuristics anyway, we have used a different heuristic, which is called assumed density filtering. And basically is a heuristic to get from, if you know your input expectation value and covariance, how do you get your output expectation value and covariance? By propagating Gaussian distributions. So we assume at every step in the network, in every layer, that we have a Gaussian distribution. How does this look like? So you start with an input distribution that is a Gaussian. The first linear transformation will leave it as Gaussian, so you can calculate the transformation directly. Then you apply some ReLU that will, of course, cut off some probability weight and push it to the axes where the values are 0. And then you do a projection back to the nearest Gaussian, nearest in the sense of the Kullback-Leibler divergence, which basically amounts to moment matching. You just take the moments of this, the first and second moments of this distribution, and just replace it with a Gaussian of the same moments. And that's how you get an approximation, by propagating this to the network. But of course, this approximation will only be heuristically good. It will become, of course, worse as you go along, because the output distributions are very intricate and they will not be matched by a Gaussian distribution. Question that we asked ourselves was if there is maybe a cleverer distribution than the Gaussian that could actually be propagated exactly. But we have shown that for any dimension larger than 2, the only distributions that are invariant under ReLU neural network layers are indeed sampling distributions or finite support, which basically amounts back to sampling. So, all right, but the good news is that assumed density filtering is differentiable, and that means we can just optimize our kind of vector S via gradient descent. So this is how we want to design our practical algorithms, and that's what we did. And to show that this algorithm has some merit, we now go to numerical evaluation. So just a short recap. So rate distortion explanations are basically defined of, you define this rate distortion problem, you do a convex realization, do a Lagrangian of this convex realization, and then you optimize S via gradient descent and with the ADF, assumed density filtering. We first calculated the rate distortion functions for the MNIST data set. Here we trained a network to a high test accuracy. You can see the network architecture on the right side. MNIST just handwritten digits. And you can see some examples here for the number 6 of different methods that have been put forward. There's RDE and 2 methods, diagonal and low rank, where we basically, that describes how we propagate the covariance matrix, whether we only take diagonal values or whether we take a low rank approximation because the whole matrix is just computationally infeasible. But both methods normally give something very close to each other. And you can see our method says, okay, this gap there in the top right for the 6 is important. The other methods, smooth grad sensitivity, also focus on this gap a bit, and some just highlight the 6 itself. And as you can see here, you now see the rate distortion for the ordering that was induced by these relevance maps. And you can see that our methods do achieve substantially lower distortion for the same rate. Let's look at a bit more complicated data set. This is the SDL10, which has 10 classes of animals and vehicles. And we also trying to test a test network that you can see to the right. And here the situation is a bit different. Here are some example images of dogs. You can see ours is relatively sparse compared to the other method. And you will see this also here, that now for very sparse rates, our method is again has the lowest distortion. But if we go to higher rates, the method kind of stalls in quality and other methods become better. And that is because, well, in the Lagrangian formulation, you kind of still optimize for a specific rate dependent on this tuning parameter lambda. And in the meantime, there have been some projects of my colleague where he basically did a procedure where they optimize over the whole ordering and not just for a specific rate. And there you can see that kind of this is almost always the best for compared for every rate if you optimize over the whole ordering and not just for specific rates. Then we have another experiment where we said, okay, it's not always clear what the ground truth is, but let's do this binary string that I showed in the very beginning that checks just for k consecutive ones. You can actually handcraft this and just write a two-layer neural network yourself, so you know how the network thinks and what the prime implicants are. And here you can see two examples of binary strings and the methods that what they thought were the important parts. The network should find 5 consecutive ones, and it's always clear where these 5 ones are. There's only one block of 5 ones in the left and the right picture. For the left, all the methods that we could compare to or also find this block. But for the right, there are some methods which rather focus on like an almost block of where some piece is missing in the middle here, this 0. And but our methods still focus on kind of these this block of these ones. Why have I shown before so many methods and now only 5? The reason is that most of these methods kind of use gradients to calculate the output. And if you handwrite this network, the gradient will at 0s and 1 input almost always be 0. And that's why all these other methods just gave constant 0, and they were not able to work with these methods with these networks that only have like some regions where they quickly change from 0 to 1. All right. And then the last comparison that I want to talk about is this comparison with a neural network that was trained to play Connect 4. And we had like a little setup like this. Basically a 2 versus 2 setup. You had a team of a masker and a player. The masker is allowed to select a part of the Connect 4 board that he wants to show to the player. And he's allowed to show like the color features. And the player is then required to make his decision based on the color features that he sees, make the best move. And then it passes over to the other team again with the masker and the player. And the idea is that if the masker selects more important parts of the game pieces, then the player will be able to make a better decision. And we trained, the good thing here is with this setup, we were actually able to train on the hidden information already during training, which is nice because then for the evaluation, you can stay on manifold, which is good because sometimes going off manifold by replacing regions with noise will throw the network off a bit, and then it's not really clear these outputs then mean. Here you see for one board situation what the agent would be doing in the first row. You see the move, so he foils basically the row of 4 circles that his opponent could make if he doesn't put his X there. And there you see in color on a color scale what the different methods think was important for this move. And then in the second row, you see what if we only show the 50% of color features according to the method that the method thinks are the most relevant, and then which move the agent would make if they were shown this only this percentage of color features. And you can see for most of them, it's the same move. He would always foil these 3 rings. But sometimes, so for example, LRP doesn't show this 3rd ring here, so he doesn't know that there are 3 rings in a row, so he makes a different move. And for random, it's just a random method, shows some random color features that he would put the cross somewhere completely different. On all others, he basically stays with his, he lets the move unchanged. And then we were able to do a big tournament between all the methods. The agent is always the same, it's the same method, but the pieces that he gets shown is selected according to the saliency method. And you see there's kind of like a leading pack of deep shape, guided backprop, and RDE, which perform all almost equally well. And then a different pack of gradient, LRP, and deep Taylor, which are kind of like in second place. And then smooth grad does not have a good time because it also samples gradients. And these gradients on, if you train on kind of discrete inputs, are not very helpful because the gradients are not necessarily evaluated at discrete points, and then they don't really tell you anything about the network. All right, that already brings me to my conclusion. And what have we seen so far? So useful definition of the saliency maps. Yes, we can do that. We use the prime implicants, and we use this array distortion formulation to kind of define the saliency maps as a greedy approximation of the optimal array distortion function. Then practical algorithms. We have shown that we can practically produce these maps by using convex relaxation of set membership and assume density filtering to calculate expectation values. And then for a numerical evaluation, we say, okay, let's compare these methods, explicitly calculate the array distortion functions for different scenarios, use handcrafted neural networks where you already know what the network reasoning is. And you can even use competitive games to let them kind of play directly against each other. All right, that was my talk. Thank you all for listening, and I'm now open to questions.
Okay, thank you very much, Stefan. Yeah, the floor is open for questions. Go ahead. Or I can start if nobody wants to start. So Stefan, now that we've got these heuristics in there, what kind of guarantees can we give about you know, these probabilistic explanations? How easy? I mean, we're very interested in giving explanations for systems and critical applications, and we want to be right. And yeah. So what happens here now? What happens to that question?
So I think deriving these guarantees for something like these neural networks is really hard. So I think the only ways out so far are use simpler decision models. So it has been shown, for example, by the group from Zhao, that for these decision trees, there are algorithms that give you succinct explanations. But for neural networks, I think our results show that efficiently you cannot really give guarantees, so it will not be possible. There is still some way out. So there has been another group which has relaxed the problem even a bit more and said, okay, it doesn't have to work for each network and each input, but rather for a given network and with high probability for a random input. And then they actually derive some algorithm that works in polynomial time. The problem there is that the map size, the size is kind of some polynomial in the optimal size of the set. And this polynomial is extremely large, and to be used for the input dimension would have to be magnitudes of order bigger than the optimal prime implicant set. And then also this, in this sense, this algorithm also does not yet help because if it cannot be made smaller, it will just cover the whole image all the time. So that also doesn't help. So the only last way out would be that we are looking still at a too powerful function class. The general neural network are still too powerful, and they are not what we actually would get if we train on real world data. So I mean, training a neural network is also NP hard, or NP to the PP if you have some probabilistic guarantees. So the last resort, I would say, is somehow find out properties of this function class of networks that are trained on real life, that can be efficiently trained on real world data, or have been trained on real world data, and give some guarantees for this type of network. But at the moment, no one understands what these restrictions are. So they are not in restricting the size of the weights. They're not in sparsity. They're not in restricting the depth, except if you reduce the depth to 1. So that is actually something I think about oftentimes. What are the properties of the network that basically makes all these hard problems somehow doable? Because a lot of these methods do work, and they work in a lot of circumstances. So the question is, yeah, why do they work? And but we're very far from that, I think.
Okay, thanks. Other questions, remarks?
Do you have translational invariance, like in images, in digits? Usually, if you run convolutional neural networks, if image is translated, then the support, right, of the decision that you look for should also be translated. So is your approach like, can that property be induced in your approach?
So I think we have to differentiate between what is commonly known as this like global saliency maps that basically tell you which parts of the input are generally relevant independently of a concrete input. So for example, if you have a picture with a boat, oftentimes the boat is in the center of the image, and you can say that already without seeing an image of a concrete boat. Now, once you are given a concrete image, then this translational invariance is kind of resolved because the boat will be at a certain place. So if you are interpreting a concrete image, you will not have this translational invariance anymore. But this translational invariance also is the reason why these interpretations only make sense for concrete inputs. If you want to say, okay, I have any image, where do I normally need to look to find a dog? Then you will not be able to answer this, except you can look everywhere because it's translationally invariant. For some other data that is not translationally invariant, like maybe medical data or so, you can say, where, if I want to check, where do I have to look to check for, I don't know, pneumonia or something? And then you can say, okay, I have these 3 values here normally are indicative of this. But I would say for images where you have this translation invariance, the question doesn't make so much sense anymore, and you have to go to the concrete input, and then the translation invariance is not there anymore anyway. Does that answer your question?
Yeah, okay, thank you.
Rufin? No sound, Rufin.
Yes, excuse me, I pressed the wrong button. Yeah, so the problem that you're looking at seems to be always in the providing an explanation in the input space, right? So for images, looking at pixels, etc. But isn't it interesting? And aren't there cases where the right level for the explanation might be more in feature space, either the features of the network itself, or maybe another feature space based on, I don't know, Fourier transform or anything? I mean, is the pixel or the actual input always the right domain?
Okay, there are kind of 2 aspects to this question. The first is, what kind of models are we working with? Are we going into the kind of modern framework of, okay, don't predefine anything, let the network figure out everything for itself? Because there was kind of the area before that where people were still handcrafting features. They were still saying, okay, we take kind of bundles of regions or so and input that as features, so that the input domain is something that is not on the pixel level, but already on a higher level. And what normally it converged to was that, okay, that doesn't help. Let's just let the network figure out its own features. So then if we have made this choice, let the network figure out all the feature levels by itself, like craft the pixels together to edges and so on. Then the question is, if we want explanations on a higher feature abstraction, what do these explanations correspond to then? So what I mean is, with how are we able to connect a node that is inside of the neural network to a concept that humans can understand? There are actually people working on this. There's, for example, this circuit distillation of Chris Olah. I don't know if you know about this blog, where it basically tries to look inside of the network and attach these nodes in the network with human-like concepts by looking at, okay, what gives you maximum activation for this node? And then normally there appears something like a dog faces all over the place. And then you can say, okay, this is a node that recognizes dog faces. So if we are able to link internal nodes to human-like concepts, then I would say it makes sense to also kind of propagate the relevance to these nodes and then say, okay, this node and this importance, and this node corresponds to this and this concept. If we are not able to link the nodes to understandable concepts, then this number won't tell you anything. It will just tell you node number 35 has a high relevance value, but that won't tell you anything then. So in the sense that maybe we're able to link these nodes to concepts, and then these explanations would make sense on higher level features.
And just out of curiosity, the method would work, of course, in another feature space, right? So in layer 4 of your computational network, you could apply exactly.
Yes. That would normally, you would just have to you would add the noise then on that level, and you would define the convex. You could define anything on that level then and optimize the S, so the set membership vector. Also on that level. There are some people like my old supervisor, Gitta Kortiniuk, and her group, who has done this on the wavelet domain with the idea that images are kind of sparse in the wavelet domain. So wavelets correspond to maybe interesting features, and then we can just say, okay, let's optimize these maps on the wavelet domain and just feed wavelets into the vector. But I think in the end that doesn't. Yeah, you can do many of these things, but I don't think there's yet a big difference in much maps.
Thank you.
Other questions? I want to go back then, if nobody wants, I want to go back to this question about untangling robustness a little bit from explainability. You said you had something more to say about this. I mean, for me, well, for many of us who work on explainability here in Toulouse, those two issues are very intertwined because the same kind of techniques that allow you to, find an explanation will also tell you something about the robustness of the system, and you've shown it yourself, right? That these prime implicant methods often turn up adversarial examples, right? But yeah, so you wanted to say something more about it, and maybe you already did, but one of the techniques you might think of is, one of the generalizations you might want to look at is that a lot of the adversarial examples are very artificial. They're out of the natural training domain, and maybe that goes back to that remark that you had about maybe we should just look at machines that are trained on naturally occurring data, on real data, so to speak, rather than these constructed examples, and not. But it seems to me that somehow we want to cleave apart this problem of robustness and explainability. I've always thought that even if you have some crazy explanation that shows up, let's say that you're just looking at that QR code or something on the bottom of the picture that you were showing us, that shows us that, okay, that classifier is not a good classifier, right? It's doing something that it shouldn't do intuitively. It's picking up on the wrong, and so those explanations are extremely useful for our understanding of the machine. So I wouldn't want to get rid of them either. That's the other thought I have about this, and why I kind of think that the two issues, though related, really need to be distinguished. But I'd really like to hear your take on this sort of amorphous set of concepts that I've thrown at you.
So I'm not 100% sure that I understand the question.
Yeah.
Could you just maybe?
It's more of a feeling. It's not a good question. I mean, my feeling is that robustness and explainability are related but distinct. Okay. And so your main motivation for going to this method was saying, well, our classifiers aren't robust, and we want to look at certain
okay.
subclass of explanations. But my feeling is, actually, we want to understand these explanations that show us these adversarial examples too. We want those because they tell us something about how bad those classifiers are and where we have to fix things. And so,
Yeah.
okay, yeah. And so in some ways, I want to question this sort of point of departure once again.
Okay, so I think I understand now the question. I would answer this in the following way. The question comes down ultimately to what we see as the input domain of the classifier and where we want the classifier to work. So the question of robustness, or there is kind of this assumption that to train the classifier, I want it to work well on a certain manifold. It's not really in a mathematical sense, a manifold like a data manifold. And on this manifold, I want the classifier to discern between images.
Mm-hmm.
Maybe classify images. So to do this, I sample from this manifold. So I sample images and train the classifier on it. Then the question is this, the classifier performs maybe in a test data set very well. The question is that a good classifier then? And you might say, okay, yeah, because it generalizes well to other images of this from this type. But from a robustness perspective, you might say, yeah, but if I just change a few pixels, it's completely thrown off and says something nonsensical. Mm-hmm. So the question now is do you accept this classifier as a robust, as a good classifier? And from the perspective of robustness, from this question on, you might say, no, I'm not happy with this classifier. I want it to be more robust. I want it to be that it gets not thrown off by just small deviations from the data manifold. From a different perspective, if you say, okay, I'm using this network to do some tasks and works well, and it makes decisions for me that are good, that perform well, I'm not interested in, I'm not requiring the input domain to be larger than what to be something else than I use. Can I still explain this classifier to get some insight on how it reasons on the input domain? Mm-hmm. So, and then I would say, for me, these questions are a bit distinct in what you require. So I think that the question of robustness is something I'm not happy with, a classifier that only kind of works well on a very slight and intricate manifold. And I want it to be more robust. And the other question is, I am happy with this kind of classifier because that is what I want to use the network for. And I still want to understand its reasoning in this regard and still want to interpret it. So if you say, no, I am only happy if it works on a much larger area of the possible image or a much larger input space, then I think you must solve the robustness problem beforehand before you can start to interpret, actually.
Okay. Yeah. Okay. I that's very helpful. I think my intuitions go in that way, that I want to solve the robustness problem before I interpret.
Mm-hmm. Yeah.
Okay. Okay, great. Other questions or remarks? I can't see all of you, so if somebody just speak up. Well,
so I think there was someone who wanted to ask something more about these complexity results in the very beginning.
Okay. Yeah, who wanted to talk about that? I guess you must have answered their worries.
Maybe. So let me just add something like the last aspect that I also oftentimes get asked, and that I think people are sometimes asking later about, and that also, like, if you write something in this area, oftentimes gets asked by the reviewers. So, for example, why is this definition even sensible to fill up something with noise, for example? If you say, okay, you send to Bob this area of the image, should Bob really fill in the rest with noise, or should he have some smarter in-painting routine that kind of fills in the rest of the image with natural, like extend the image to like a natural, or the part to a natural image again. And I think this is a valid criticism of the definition, also of the method, because you are going off manifold, and there the robustness aspect is pretty important, because suddenly you're evaluating the network outside of the domain that it is trained on. So how much do these values even mean that the network gives back? On the other hand, there's also the problem that if you have a generator to do this, and normally it can only be done with generators to in-paint the rest of the image, this generator was likely also trained on the same data. So the same biases that are in that the classifier has, the generator might also have. So for example, if in the image there was always boats on water, and you send to Bob a boat, then the generator might always in-paint the water again. And then even if the classifier only looks for water, you would suddenly see that the best prime implicant might be a small boat, even though the classifier only looks for water, because the generator is actually helping the classifier by providing the link between water and boat. And that can also throw you off. So you kind of, if you are very data-driven, you can get one set of mistakes, which is like you're too close in your correlations, or the correlations are too strong. And if you're very non-data-driven, just stupid noise, you can get another type of mistakes, like going off manifold and then sometimes getting weird results. And I think at the moment, there's not really, I don't know of any yet Goldilocks solution that is kind of solves this completely. So interpretability, also in what I've learned kind of over the course of the PhD and doing all these projects, without having a good idea of the data manifold, is very, very difficult to define without running into some kind of problems.
Yeah, I think that's right. I also, there's this group of people at AXA in Paris. They have a AI group. One is Logel, another Thibault Logel, and a Polish guy, Dyszynski or something, and they kind of concur with you, I think, also about this idea of trying to stick to this the real data point of view. I don't know if you know their work. It might be interesting.
No, yeah, maybe you can send me some link also. I would looking
okay.
a bit of that.
I will. Okay, well, I think, I don't know if anybody else have any questions or remarks. If not, I guess we'll go ahead and close the session. Thanking you once again, Stefan, for very, very, very interesting talk. Gets at the heart of many, many important issues. So that's great.
All right, thank you. Thank you for your time.